Hello, this is going to be a video walkthrough on problem 1 on CS61B Spring 2021 exam prep discussion number 6. So this question, we'll be talking about asymptotics, and I made a quick asymptotics introduction video earlier talking about notation. So if you guys are a little bit iffy about notation, I recommend watching that video before diving into this question. Okay, so this asymptotics introduction problem faces two of the most common sums we'll see in the class. So I definitely recommend, if you guys didn't get it, spend the time, really understand what I'm going to say in this video, because these two sums will be very common in upcoming problems in asymptotics. Okay, so diving in, this question states, give the runtime of the following functions in big theta notation. Okay, your answer should be as simple as possible with no unnecessary leading constants or lower order terms. So what this thing is saying is that if we calculate our runtime somehow, let's say it's exactly n squared over 2 plus n, okay? So what we can do here is that we can ignore lower order terms, right? This is a lower order term, so we just ignore it. And we can also ignore constants. So this function, if this is its exact runtime, we would think about its runtime proportional to n squared. Okay, so that's what that second bullet point or second sentence is really saying. Anyways, okay, so for the first function, we have some method f1, and what it's doing, it has a nested for loop, and the important thing is that the second for loop goes all the way up till but not including I. Okay, so let's try to figure out some sort of way of approaching a solution to this. For me, I think the best way is that let's create a little chart. So in this chart, we're going to have two columns. We'll have I, and we'll have the amount of work we do for that value of I. Okay, so when I is equal to 1, I'm going to say work is how many times this thing is printed. Okay, so when I is equal to 1, we actually don't print it at all, so it's 0 work. When I is equal to 2, we print it once. When I is equal to 3, we print it twice, right? When I is equal to 4, we print it 3 times, and so on. And what we'll notice is that if I is equal to n, we'll print it n minus 1 times. Okay, and how did I get these numbers on this column right here? Well, notice that, let's just say that I is equal to 4, right? What'll happen is that this for loop will look like j is less than or equal, or j is less than 4. So then this thing will get printed when j is equal to 1, 2, and 3, right? Okay, so with this in mind, to find the total amount of work this function is doing, all we really need to do, which is really cool, is figure out what the sum is of this column right here, right? Because if we figure out what the sum is equal to, we know that's the total amount of work this function is doing. So let's try to figure out what the sum of this column is. And how we can write it is 0 plus 1 plus 2 plus 3 plus n minus 1. Okay, and for simplicity, just to like make it a sum that we'll see more often in the course, this is basically the same thing as 1 plus 2 plus 3 plus 4 plus all the way up till n, right? It's basically the same thing. I just added another n, which doesn't change anything asymptotically. Okay, so looking at this sum, what is this sum equal to? Okay, because if you figure out what the sum is equal to, we'll figure out what the runtime of f1 is, right? So to try to figure out what the sum is equal to, there's a couple ways of solving this. The first way is we can just memorize that whenever we see the sum, it means n squared asymptotically. And this, for the sake of this class, will work. If we ever see the sum of the first n numbers, we tell ourselves that's n squared. But for me, I like to intuitively reckon for why this is the case, okay? So suppose that we have the following sum. What I'm going to do is I'm going to rewrite it as 1 plus 2 plus 3 plus 4 plus 5 plus 6, okay? And I'm going to say in this example that n is equal to 6. Okay, so to figure out the sum, there's something cool that we can do. We can group terms from both sides together. So if we group 1 and 6 together, 1 plus 6 gives us 7. If we group 2 and 5 together, 2 plus 5 gives us 7. And then if we group 3 and 4 together, we could see that gives us 7 as well. And what we will notice is that if we ever have a sum of 1 plus 2 plus 3 plus 4 plus n minus 3 plus n minus 2 plus n minus 1 plus n, sorry, it's a little cramped at the end, what we can always do is we can kind of group the first and last terms together, right? And we can keep grouping as we iterate down. And what we'll notice, which is really cool, is that how many of such pairs, like we can define this to be a pair, do we make? Well, looking at this example, we can see when n is equal to 6, we have 3 pairs, which makes sense because each number is involved in one pair and there's 6 numbers. So what we can say is that there's n over 2 of these pairs, right? And each pair has value 7 in this example. How did we get 7? Well, that's the same as saying n plus 1, okay? So what we notice is that the total sum of 1 plus 2 plus 3 plus 4 plus 5 plus 6 is equal to n times n over 2 times n plus 1 in the general case, right? And with that in mind, what we can say, going back up here, is that this sum, that's the one we wanted to find in the first place, that's going to be equal to n times n plus 1 over 2, okay? And asymptotically, if we look at the sum, that's the equivalent of saying n squared asymptotically if we ignore lower order terms and we also ignore leading constants, okay? So the runtime for the first one is going to be n squared, right? And the quick reason is that this sum asymptotically is n squared. The long reason is that if we look at this sum intuitively, if we group the first and last terms together, we see they sum to n plus 1 for every one of these pairs, and there's n over 2 of these pairs, giving us n over 2 times n plus 1, which asymptotically is the same as n squared. Phew, okay, that was a good amount of work. Let's move on to the next one. Okay, so for this next example, I'm going to proceed in the same manner I proceeded for the first one. What we're going to do is we're going to create a table, or not a table, this little chart, where we have I here, and then we have work on this hand side. And now what we're going to do is we're going to say for every value of I, how much work are we doing, right? How many times do we print out hello, Hannah? Okay, so when I is equal to 1, we never print out hello, Hannah, right? Then when I is equal to 2, right, this is how I changes over time. So we can see for every value of I, similar to the first example, we're basically doing I minus 1 work, right? So for simplicity, I'm just going to say that the amount of work we're doing is proportional to I, right? So just for to making the numbers easier, let's just add 1 to each of these. It's a nicer sum, okay? So the total amount of work that we're doing in this function is going to be the sum of this column over here, right? It's going to be the sum of all of these numbers. Because each time in this for loop, the amount of work that we're doing is proportional to the value of I, right? So we need to figure out what is the value of this sum. So to figure out the value of this sum, let's expand it out again, similar to the first time. So we'll see that that's the same as saying 1 plus 2 plus 4 plus 8 plus n, okay? So to look at the sum, again, there's 2 ways that we can kind of approach its value. The first way is I can just tell you that this is asymptotically on the order of n. And for the rest of this course, you can just memorize that, and that's totally okay. I like to think about it I like to prove it to myself why this is the case. So what we can say here is that if we ever have 1 plus 2 plus 4 plus 8 plus n minus 1 plus actually, let's do, my bad, this is incorrect, plus n over 2 plus n. What I'm going to argue now is that the sum of these numbers is going to be n minus 1. Okay? So to see why this is the case, let's say that n is equal to 8. Let's do 16. So we see the sum becomes 1 plus 2 plus 4 plus 8 plus 16, and we see the sum of these terms is 15. Okay? So we can see here that if we ever have the following sum, we know that all the terms except for the last term sum up till n minus 1, right? Which means the total value of this sum is n minus 1 plus n, which means that it's roughly on the order of n, right? So what we can say is that when we look at this sum, it's asymptotically on the order of n. Okay? And I like to think about this sum, it reappears in different forms, but the way I like to coin it is that it's a dominating sum. Okay? So that's my terminology for it, and I'll explain why this is the case. So a dominating sum is a sum where the last term is all that contributes to the runtime. Okay, I'll say that again. So a dominating sum is such that the last term is all that contributes to the runtime, so we can ignore all terms before the last one. Okay, so there's other examples of dominating sums. Another example is 1 plus 3 plus 9 plus 27 plus n, right? Anytime that we have some sort of multiplicative factor, right? If we ever multiply by some value greater than or equal to 2, we can see that we have such a dominating sum, in which case the last term is the only term that really contributes to the runtime. So this was a bit of an aside, but I think as you guys approach asymptotics problems in the future, this idea of if I recognize a dominating sum, I only really care about the last term when I calculate the runtime is really important going forwards. Okay, so yeah, with that in mind, we can say that the runtime is n for the second function f2. And that is all for this video recording. Stay tuned for problem 2, which will be covered by Shreyas, and then problem 3, which I'll cover. Yeah, I'll see you guys in the next one.